So far we've only been looking at Fourier series on the interval from minus pi to pi. So what exactly do I mean by that? I mean that so far when we've been talking about Fourier series, we've been saying that we have some series given by this, and cosine of nx plus bn sine of nx. And one of the properties of this, because cosine and sine are periodic, is that this function is going to be periodic, where it's defined on this interval, minus pi to pi. And then from pi to 3 pi, it's going to look the same. And then, so on and so forth. But one thing that you might want to do, one thing you might be interested in doing, is looking at intervals that are maybe larger or smaller than this. Maybe you want to go from minus 2 to 2 or minus 10 to 10. Or more generally, what if you want to go from minus some L to some other L? How do you have to modify this thing in order to get that? Well, let's think about it, right? So we know that, effectively what you're doing when you're changing the range of your interval, what you're doing is you're sort of scaling your function. So whatever function you have on minus L to L, you could think of as you could scale it down to minus pi to pi, you'd solve for it there, and then scale it back up. And so what exactly do I mean by that? I mean that if you're going from minus pi to pi, and you have some function maybe that looks like this, but really you want it from minus 10 to 10, then what you would do is you could kind of solve for it here and then stretch it out. So I hope this image kind of makes sense. But all right, that's a lot of talk. How do we actually stretch this interval out, and how does it affect our ANs and our BNs and these terms right here? Well, let's think about it. So we know that we're going to have some same constant out in front. Our constants will change, but it'll be inside the integral. So I'll keep this AN here, and then this cosine. And then something different is going to happen. So let's think about it. And really, what I'm thinking is that we know it's going to be a linear shift. So there should be some factor of L that shows up in here. And we know that when we set L equal to pi, that is, when we set this length equal to pi, we should just get back this ordinary series right here. And so if we want to do that with something linear, there are really two choices that we have. We could either do nx times pi over L, or we could have the L on top and then the pi on the bottom. We know that those are our only two possibilities because we know that if we set pi equal to L, and so what's the other option? The other option is nx L over pi. We know that these are our only two options because it's got to be something linear, which means just multiplicative. And we know that when we set L equal to pi, we should just get back nx. And in both of these cases, when we set when we set L equal to pi, the pi's cancel out and we're left with just nx. So we know both of these work. So which one of these is it? Well, there's a second check that we could do. The second check that we can do is that when we set x equal to L, what do we expect? We expect that we should be at the very end of this interval here. And so what that means is that when we set x equal to L, we should get n pi, because normally pi is the farthest out to the right you can go, and so that's the farthest right value you can get, and so when you get x equal to L, you should get that farthest right value, and that's what happens in this case right here. If we set x equal to L, you get n pi, which is the furthest right you can be, but in this case, when you set x equal to L, you get L squared over pi, which doesn't make sense, and so what that means is that this function right here is how we generalize our interval to some length L. Okay, this is great. We've done it here for these terms. Now let's look at how we do it with the coefficients, because our coefficients should also change. So our coefficients, you'll recall, originally are given by an is equal to 1 over pi, integral minus pi to pi, f of x cosine of nx dx, and likewise for bn. All right. So okay, I mean, so this is rather straightforward to update. So we know that at the very least, we shouldn't be integrating from minus pi to pi anymore because that's not our interval. We should be integrating from minus L to L, minus L to L, f of x, and then our cosine should be the same as it was up there, cosine of n pi x over L dx. And then we have this 1 over pi out in front, but that 1 over pi that 1 over pi is the length of half the integral, half the interval, and so that should generalize to 1 over L, and so we've got a new expression for our an, and likewise for our bn, it's going to be the same story. It's going to be 1 over L minus L to L, f of x, sine of n pi x over L dx. Okay, so we've done it. We've taken our Fourier series, we've generalized it to some arbitrary interval minus L to L, and we see how that changes both in our formula for f of x and for these coefficients an and bn. The only other thing I'm going to do is do the same thing, but for complex exponentials. And you'll see, there are no surprises here. With complex exponentials, our f of x is equal to what? It's equal to some sum from minus infinity to infinity. We have some cn, and then we have some e to the I, and then same thing as before. We're going to have n pi x over L, and then the cn's right here. It's going to be the same thing as before. It's going to be 1 over 2L, integral minus pi to pi, f of x, e to the minus I, n pi x over L, dx. Perfect. So we've done it. For both our sine and cosine Fourier series and our complex exponential series, we've generalized them to be on some arbitrary interval minus L to L.